Okay, so good afternoon, everybody. It's a pleasure to introduce our speaker for this special talk, Sri Krishna Vadlamani. Sri is finishing up his PhD in the group of Ila Jablanovic at Berkeley in the Department of Electrical Engineering and Computer Science. He's done some really groundbreaking work in new forms of computing, um, and in particular, that inspires his title of physics-based machines for discrete optimization. Sri, great to have you.
Thank you.
Thanks for taking the time. I'll pass it off to you.
Thank you, Professor England, for the very kind introduction. Hi, everyone. Today I'll be talking about two different topics. The first one would be spectral broadening in tunnel transistors. And the second one is physics-based machines for discrete optimization. So the underlying theme of the two projects is basically energy saving. How do we change device physics? How do we change device structure through a study of device physics to save energy? So that's the first part. And the second part is how do we change the system design in order to save energy? So that's the underlying current behind the two projects. So let's begin looking at the first one. So this is just the structure of a conventional MOSFET. You have a source, you have a drain, you have a channel in between that is gated through a gate, and the channel barrier keeps going up and down depending on the gate voltage, and that modulates the current that goes from left to right. So that is the switching mechanism, the height of the barrier. And that turns the MOSFET on and off. So the mechanism is thermal barrier switching. So as the barrier becomes higher, the amount of electrons that you get across the barrier reduces according to the Boltzmann factor. So the transistor turns off. And as the barrier gets pushed down, you get more and more electrons flowing across, and you go to the on state. And this behavior is basically captured in the subthreshold slope. So before your transistor turns on, there's a certain region where it is in the process of turning on. So that is captured by the subthreshold slope. So right now in MOSFETs, the best subthreshold slope we can get is 60 millivolts per decade, which is dictated basically by KT at room temperature. But we want to go beyond it. So we want to bring down this subthreshold slope to a lower value so that we save energy. And that was the entire motivating rationale behind setting up this center called E3S at Berkeley. So this was set up by Professor Jablanovic 10 years ago, and this was one of the main motivations for that center. So we had three requirements for a new transistor, and they were all very ambitious. So the first one was we do not want 60 millivolts per decade anymore. We want to pull it down to possibly maybe 1 millivolt per decade. So that was the high ambition that we started out with. And we still want to maintain the very good on-off ratio that MOSFETs have, which is 1,000,000 to 1, million units of current in the on state to 1 unit of current in the off state. And we still want to have very high conductance, because you need to switch, when you switch on and off, you have to charge up all the wires, and you have to do it very fast. So if you have a high conductance, you have high current, and you can charge up all the wires. So we want these three requirements to be met by the new switch, whatever it is. So tunnel transistors were one of the main candidates that we studied. It is hoped that tunnel transistors will achieve a subthreshold slope, which is less than 60 millivolts per decade. But we also hope that they will reach the same on current as MOSFETs. So this is the sort of IV curve that we're looking at. This is the drain current and this is the gate voltage. So this is what we are aiming for. Why would we expect tunnel transistors to perform better? What is the mechanism, and why did people have this hope? So the mechanism is you have a source, you have a drain as usual, and in the channel you have in one of the most basic prototypes, you have two quantum dots. So there is this what I'm calling a valence band quantum dot and a conduction band quantum dot. So this quantum dot is coupled to the drain. The left quantum dot is coupled to the source. And when the energy levels in the quantum dots are aligned, you get current flow from the source to the drain. So you have energy conservation, and everything is good. This quantum dot is gate controlled. So to turn it off, you just apply a gate voltage. The energy levels get pulled apart, and there's no longer any energy conservation, and that's it. We are in the off state. There's no current flow. So is it that simple? Do we have an infinitely sharp switch which turns off on the application of a very small voltage? So that's not the case. There are more intricacies to it. And the foremost is that the energy levels in the quantum dots do not remain sharp. So if there's a quantum dot that is isolated from everything else, from all the surroundings, then the energy levels are going to be sharp, and this sort of naive picture works. But because the quantum dots are connected to the resistors, to the leads, the source and the drain leads, these energy levels get broadened. So there is some interaction. You get some sort of hybridization with the energy levels in the wire, and you get some broadening. And when you pull the levels apart, there is tunneling between the tail of one broadened line shape to the tail of the other broadened line shape. So you get this sort of leakage current as you pull the levels apart. So understanding this shape is critical to understanding how the IV curve changes as you change the gate voltage. So how do we find that line shape? How does it work? So we will look at just one half of the, let me go back one. Yeah. So we just look at one half of this device. So you have this quantum dot, you have this lead, they are connected to each other. And how does that interaction broaden the levels? So we'll just look at one half. Yeah. So there's the quantum dot, there's the wire, and the electrons that are leaking from the left to the right. And the way one would calculate these line shapes is using spectral line shape theory. One of the fundamental quantities there is something called an autocorrelation function. So it's a fancy term, but basically what we are looking at is if I put an electron on the quantum dot at t equal to 0, it will not stay there because the dot is connected to the wire. The electron will start leaking into the wire. So there is going to be some decay of the electron amplitude on this quantum dot wave state. There's going to be some decay of that amplitude. And we find that function as a function of time, and we take its Fourier transform. So that gives us the line shape. So here, I just have a couple of formulas. The details are not important. I'll just point out the essence of these things. So I'm saying, okay, the dot has maybe a sinusoidal wave function, a single mode with a single maximum. So when you take that and project it on the joint eigenstates of the dot plus wire, they're unknown. There are some complex superpositions of these plane waves here and this single sine lobe here. So you have some complex wave functions, which are the joint wave functions. But let us take this original wave function that we started out with, which is the electron on the dot, and project it on the unknown true eigenfunctions. So you get some superposition of the true eigenfunctions, which gives you the starting state. And as time passes, there is some evolution. And you find this autocorrelation function, which is just the dot product of the wave function of the electron at 0 with the wave function of the electron at t. And you get a very appealing function. So it's some superposition of plane waves. So these are plane waves in time. And you have these very nice coefficients. And when you take its Fourier transform, you get deltas in the energy space, and you get the weights of your original wave function on those true eigenstates. So this basically captures the intensity of your wave function on each of the true eigenstates. So that is the rationale behind taking the autocorrelation function and finding its Fourier transform and declaring that is the line shape. So when people do this, there are certain approximations that are involved to make the calculation easy. One of the foremost things is, maybe let me go back one. So they assume that the quantum wire has lots of states spanning a very huge energy range. And they also assume that the coupling between the dot and the wire is basically constant across. So the matrix element between the two, this starting state and the plane wave states here, is basically constant over the entire energy range of concern. So when you do that, and when you solve Schrodinger's equation, you basically get a pure exponential decay of the electron amplitude on the dot. So the electron amplitude started at 1 because it was fully on the quantum dot state, and then it decays exponentially with time. So this exponential decay rate is given by Fermi's golden rule. So this is the type of decay we get. So we get an exponential decay, which starts out as a straight line, as a linear term at t equal to 0. And this is the energy shift term because of the interaction between the wire and the dot. So the dot energy gets shifted slightly. And when you take the Fourier transform of that exponential decay, you get a Lorentzian function in energy. So yeah, these are just some additional things, but the basic structure of the Lorentzian is 1 by e squared. So 1 by e squared is the characteristic behavior of the Lorentzian. So at the center of the band, at the center of the dot energy level, you have the peak, and on either sides, the dot energy level gets broadened in this Lorentzian shape. And the Lorentzian shape falls off very slowly. So if you notice, it's 1 by e squared. So if you plug it in log scale, the strength of basically the density of states versus the shift from the center of the dot energy, the line shape falls off very slowly. And it actually flattens out because of the 1 by e squared behavior. So this is a bad thing because we originally had exponential line shapes in MOSFETs for the IV curve, but here we have Lorentzians in the broadening. So we'll have to compute the IV curves to see whether this Lorentzian has a bad effect. But yeah, let me give you the answer. It is going to spoil your IV curve. It's going to give you Lorentzian IV curves. When you have Lorentzian broadening of your energy levels, then the IV curve is also going to be Lorentzian. So you have leakage from one quantum dot, which is Lorentzianly broadened, into another quantum dot, which is again Lorentzianly broadened. So you have this electron here from the source side going into this heavy Lorentzian tail. And because you're going into that heavy tail, you never switch off. How much ever you pull this thing up using the gate, you will still see a heavy tail, and the leakage doesn't drop that quickly. So what we would actually want is an exponential line shape on the quantum dots. And that is when we can at least start comparing with MOSFETs. So right now, this sort of TFET is so bad, it doesn't even compare to MOSFETs because of the characteristically different turnoff. It's a Lorentzian turnoff, which is much slower. So yeah, that's what we are saying here. If you have Lorentzian tails, you can never turn off the tunnel transistor. So how do we get these exponential line shapes? So that's the fundamental question. Yes, so I'm just saying yes, Lorentzians do not satisfy the first condition. They do not satisfy the second condition. We never turn off. So yeah, we thought about this in various directions, and the final most appealing direction that we hit upon was let us assume that the final density of states in the wire. So you're tunneling into a wire, right, from the quantum dot. So let us assume the density of states in the wire is spread out only in a thin range of energies. So it's not spread out across all energies. It's just a thin range of energies. So yes, so maybe I should explain this graph. So on the x-axis, I have energy, and on y-axis, I have either density of states or the density of probability of tunneling into as a function of time. So so this sinc function here, this is a sinc squared function. It basically tells us how much of tunneling probability that an electron has at a particular energy. So at the very beginning, at small times, this is the spread of electron probabilities into the wire. And as you let time pass further, so as you go further in time, the sinc squared becomes thinner and taller. So you get a delta function, and that's the delta function that appears in Fermi's golden rule that helps us conserve energy. So initially, so the way you would get the population in the wire at a fixed time is just integrate this density of states with this probability per unit energy of the electron tunneling. And you would get some electron population in the wire. And the height of this sinc function increases as t squared. So initially, this slope is very fat. The height increases as t squared. So the population in the wire increases as t squared because the density of states is constant, and this height goes as t squared. And afterwards, you reach the delta, and you get the standard exponential decay. So basically, the bottom line of all this is when you have a restricted density of states, the population of the electron in the wire increases as t squared at small times. And that means the population of the electron in the quantum dot decreases as t squared. So yeah, so this is the new blue colored line that we get for the time decay. Instead of a purely exponential decay, you get again exponential decay, but at t equal to 0, it's not linear. So if you zoom in, you see that red is linear. If you write down the Taylor series, you get t squared, t cubed, and so on. But when you write down the blue one, you do not get the linear term in t. So this is a t squared term. And when you Fourier transform this sort of function, a function which is starts out quadratically and also goes exponentially at long times, because at long times it's supposed to go exponentially. That is what is observed through Fermi's golden rule. So when you Fourier transform this sort of thing, you start getting exponential line shapes. So the tail becomes sharper. It becomes linear in log scale, and the coefficient of the tail, the decay in frequency domain, is decided by the period of initial parabolic decay. So this initial period of parabolic decay that controls your tails in frequency domain or energy domain. So that was the basic thing that we recognized, and we said, okay, we need to modify the TFET. This sort of TFET won't work because you will have Lorentzian broadening, and that messes up things. There has to be an intermediary between the quantum dot and the big band wire. So essentially, there has to be a narrow band wire in between that connects the quantum dot and the big band wire, and that will enforce an exponential line shape on the quantum dot. So where do we get these narrowband wires? So Professor Louis here at Berkeley analyzed some graphene nanoribbon systems. I think this is called an armchair nanoribbon. And they did ab initio calculations, and they found out that this sort of system with some number of units is going to have narrow bands when they do the electronic band structure calculation. So I think this band is, they told us this was like 6 milli eV in width. So this sort of band would be very good for our device proposal. So this is the modified structure that we are proposing. You have the quantum dots as usual. You have the metal contacts as usual, and you insert these narrowband wires made of possibly graphene nanoribbons, possibly something else that is narrowband, and that should enforce a sharp spectral shape on the quantum dot. So yes, so once you have your spectral shapes, it's sort of straightforward to compute the currents. You just have to calculate the tunneling between the two line shapes, and you can also take the thermal populating of the quantum dots into account, and you will get some sort of convolution. So you just have to compute that, and when you have Lorentzian line shapes, you get a Lorentzian IV curve, because Lorentzian with the Lorentzian gives you Lorentzian in the convolution. And when you have exponentials, you do get an exponential line shape in the IV plot. So if we assume that the thickness of the narrow band in the narrow band wire is let us say maybe 5 MeV, then the slope turns out to be something like 6 millivolts per decade. So yes, so this is a very sensational result. It's still a bit controversial because the line shape that we proposed, it comes up when we make certain approximations and certain assumptions on the time decay. So it's not very clear. So right now we have like 2 viewpoints on it. One of it is we'll have to very specifically engineer the narrowband wire in a certain way, and that is when we get this sort of nice exponential line shape in frequency. So that's one viewpoint. The other viewpoint is maybe that's not really necessary. Maybe any sort of narrowband wire will do. It doesn't have to be specifically engineered. So that's the second viewpoint we have right now. We have tried to derive this sort of line shape from non-perturbative using non-perturbative Green's function methods. We got some expressions, but yeah, at some point we again had to make some assumptions, and it wasn't clear how to proceed and what sort of assumptions to make. So if we do make certain assumptions, we can get here. But yeah, that gets us to the question of whether this is general or the wire has to be very specifically engineered. So we sort of prefer just intuitively we prefer the general viewpoint, which is you do not have to very specifically engineer the nanoband wire. A narrowband wire, any narrowband wire will do. A reason for that is the existence of Urbach tails in optical communication. So by Urbach tail, I mean optical absorption in glass. So let me just start out with an example. Optical absorption in glass is actually very low in the communication frequencies, and that's why we have communications today over like across continents. But if the absorption line shape in glass had been Lorentzian, as the Drude-Lorentz model predicts, then we would have had optical communications only over 1 meter instead of 10,000 kilometers. So this is a calculation we do in class here in one of our classes, optics classes. So it turns out that if you assume a Lorentzian line shape for glass, glass has some absorption somewhere in the ultraviolet. And if the tails were to fall off very slowly, then at the communication frequencies you would have this huge loss, and it would have been impossible. But the actual observed value is much lower for absorption in the near in the communication frequencies. So there is a sort of mystery here, and the exponential nature of absorption hasn't fully been like satisfactorily explained so far. So yeah, this is the Udbag tail I was talking about. In semiconductors, this is for gallium arsenide. You have absorption going up all to the band up to the band edge. So this is the band edge, and everywhere above it you have absorption. And below the band edge you have absorption going down exponentially. So this exponential behavior is observed in all semiconductors, even if they are pure. So there is some sort of phonon disturbance that is causing this broadening of the electron state energies, and this broadening is observed irrespective of structure or basically in all the semiconductors, almost all the crystalline semiconductors. So because of this general behavior, we were motivated to think that the exponential line shape might be more general than it seems, and any sort of narrowband wire would do. So that was the rationale behind assuming that most wires should do, without like very specific engineering with the matrix elements or density of states. So that ends the first part of my talk. So I will talk about physics-based machines for discrete automation in the next part. So should I go ahead, or does anybody have questions, or do we do the questions at the end?
I think we normally do the Are there any questions? If not, I think people would normally have made them in the chat. So I think we can probably just move forward. And then
okay, yeah. So in the second part, I'll be talking about how to use physics to solve automation problems.
Actually, I'm sorry to interrupt. I did have a question. So I was wondering a couple of things about the nanowire, the nanotube is limited by the quantum conduction in one channel, right? So you're always going to have h over e squared resistance, or like 25 kiloohms. And I wonder if you thought about that. The other thing is that none of this sort of Coulomb blockade, and I was wondering how that comes into the calculus. I mean, it seems that would be important in a small quantum dot.
So to answer your first question, yes, I understand. So we'll if the wire has just one band in it, you'll be limited by the quantum of conductance. So the way we thought of dealing with it was basically putting packing lots of these things in parallel, and that basically increases your conductance. So I think that's one of the standard ways that people increase conductance when they talk about nanotube transistors. So that was the structure we had in mind. So you have, this is just a single transistor, but you pack lots of them in parallel.
I see.
Yeah. So and the second one, I'm sorry, could you please repeat your second?
I was wondering how Coulomb blockade affects what you see.
Yes. So I think yes. So you'll get Coulomb blockade if the electron here doesn't very quickly go into the wire. So if it stays here for long, then the levels get disturbed and you lose conductance.
I mean, sort of the limit for Coulomb blockade is also sort of the quantum conductance. So if you're, if you have a resistance from the dot to the channel that's greater than 25 kiloohms or whatever, then you expect to see Coulomb blockade.
Yes. So the way we thought of it was, yes, I think I understand your question. So the way we thought of it was, so let me go back to, this picture. So in this picture, the dot is more strongly coupled to the wire than with the neighboring dot. So the interaction between the dots is weaker than the interaction between the dot and the wire. We are in the like sort of weak coupling regime. So I think the electrons should leak faster into the wire than they come in from the left-hand side. So it's possibly not a problem.
I see.
Yeah.
Okay, thanks.
Yeah, thank you. Yeah, so let me start the second part of the talk. So yes, here I'm just motivating automation. I'm sure like people don't need a motivation, but yeah, it's there everywhere today. It's there in deep learning. It's there in circuit wiring and lots of other problems, RL and computer vision and so on. And it turns out that many of the difficult problems that people have today, the NP-hard problems in CS, they all map onto basically the icing problem. The icing problem is a nice physics problem, and all the difficult like circuit wiring and uh, the IEOR types of problems, they all map onto the icing problem. And it turns out that we can also map gate operations and gate, the OR gate, and the functioning of these gates. We can map all that sort of behavior also onto the icing problem. So the icing problem is essentially you have a set of spins. These are all you can think of them as just magnets. So magnets with north pole and south pole. They all have pairwise interactions. So yeah, J12 for sigma 1, sigma 2. And you have this sort of squared type of energy. So you sum up the energies of all the pairs of magnets, and you get some total energy. And you want to find the assignment of north pole up and down to the spins to minimize this energy. So you have only two options, north pole up and north pole down, which is -1 and +1, and you want to minimize the energy. So it's a discrete optimization problem. It's difficult, and the reason it's of value is lots of other interesting problems, integer factorization also. They all map onto the icing problem. So this is one of the problems that people studied, and they wanted to use physics-based methods to study this problem. So here on this slide, I just have an overview of some of the basic principles of physics, which involve optimization, and some of the algorithms that have been studied to death so far in the past that were based on physics. So the first principle is just the principle of least action. You have the action integral, which you want to minimize, and the true path that nature takes is those paths which minimize that action. So if there was some way fancifully of mapping your objective function that you were interested in minimizing, if you map that onto some action integral somehow, then you just maybe shine a torchlight, and the path of the light gives you your answer. So these types of problems are sort of easy to solve, and we can compute the path of light. So it's not a difficult problem, and yeah, but shining a torchlight is it'll give us the solution at the speed of light. So there's possibly a speed advantage there. So there is this slightly more controversial principle, which is the principle of minimum power dissipation. So here I've portrayed it a certain way, and this when I portray it this way, it's very convincing. And what we say here is, okay, there's a parallel RL circuit. There's some current I that I'm pumping through a current source. So it's always I. The input current is always I. And maybe the initial condition is such that you have 2I/3 on the left and I/3 on the right. As time passes, the currents will adjust because we have equal resistors, and you'll get I/2 and I/2. And in this state, the energy dissipation through the resistors is at its minimum. It's lower than what you started out with. So there's something happening. Nature seems to prefer lower power dissipation states. So this is there are some nuances here, but yeah, this is basically what the principle says. So those were the principles. The algorithms that people have studied are simulated annealing, which is okay, you do a gradient descent on some objective function, and to get out of local minima, you kick it out using thermal noise. So using Boltzmann factors or something, you explore the field, the solution space, and you get to some good solution. The other principle that is very common in quantum computing is the adiabatic principle. So you start out with some known Hamiltonian where you know all the states. You position your system in the ground state, and you slowly vary some parameter that continuously takes you from your starting Hamiltonian to the hard Hamiltonian of interest. And if you do it slowly enough, you will continue to remain in the ground state. So you won't make transitions. If you do fast, then energy conservation is basically not satisfied, and you have that sink function. You can get kicked out of the ground state. So if you do it slowly, you just stay there. Yes, so the quantum people were doing this, and that's very good. We wanted to. It's not just we. This line of study started maybe around like 10 years ago from Professor Yamamoto's group in Stanford. I don't think they had minimum power dissipation in mind, but they had a certain system in mind, and we will look at that and see what we can learn from it. But it basically involves the result of a study was that it involves minimum power dissipation. So yeah, so the way one would use minimum power dissipation, to solve an optimization problem is, as I indicated earlier, you have some objective function. Try to create a system whose dissipation function matches your objective function, and then just let the system run, and it will reach some steady state. In this case, this simple steady state, and that will give the answer to your problem. So that is how one would use it. But yeah, what context does this appear in, and why are we talking about this at all? So I'll answer those questions in a little while. So I want to introduce one more mechanism that has been of interest on like basically how to use physics for optimization. And this is based on laser systems. So let me see if this works. Maybe I should shift from the laser pointer to, yes. So yes, you have some laser, you have modes with some loss profiles, and you have some global gain that you're giving the laser system maybe. And yeah, so the gain gets clamped at the least loss, and all the pump goes into that particular least loss mode, and all the other modes die. So yeah, so that's the nice appealing video. So this was the motivation behind the recent surge in activity. So I'll get to what those methods were doing. So let me go to the next slide. Yeah, so we have a plethora of methods that popped up over the last few years. The first one was the method from Stanford, from Professor Yamamoto's group. And they basically have a set of optical pulses running around in an optical fiber loop. There's a nonlinear element which you pump, and that basically sustains the amplitudes of these pulses. So that's how they get gain. That's how they're generated. And you have some sort of coupling between the pulses. So each pulse here is meant to represent one spin in the Ising problem. And this side loops here, they help you couple pulse to pulse. So that gives you the Jij coupling between the spins. And the nonlinear pumping is such that the pulses will collapse into one phase or the other, and that gives you your spin up or down. So that's the overall idea. I'll get into those in a little more detail. So this sort of method inspired many other groups around the world to come up with their own methods. So we have another from Professor Roy Chaudhury's group at Berkeley. He came up with an analytical oscillator system. So Professor England's group and Professor Soleche's group at MIT came up with their own interesting optical matrix multiplier based method. And yeah, so our group, Professor Yablanovic's group at Berkeley also, we were inspired by all these methods, and we said, okay, can we do something of our own? Can we like make another system and try to analyze it or something? So we did something, and like companies are also interested, and this is an active field of work. Now there are also some methods from Cambridge. So one of the underlying underpinnings of not all those methods, but most of those methods is you have a set of bistable elements which represent your Ising spins. So the bistability gives you spin up or spin down, and your bistable elements are connected through resistors or some sort of coupling. Need not be resistors, but some sort of coupling. And that coupling is meant to perform the Jij function, which is the coupling between the Ising spins. And so yes, so we have a set of bistable analog components, and because of the bistability, we get digital answers, which is 0 or 1, up or down, and stuff like that. So let us try to understand how we get bistability in an electrical system. So let me go back. Yeah, so this was the electrical system that we studied in our group, and we wanted to see what was happening in like these sorts of systems. So we modeled it electrically. Okay, we have a spin, we have some connections. How does it work, and what is it doing? So the way you get the bistability is standard parametric amplification. So let us assume we have a simple LC circuit. So this is some noise voltage. You have a standard linear inductor, and let us assume for now that we have a standard linear capacitor. The oscillations in this can take on any phase. So we have some sinusoidal oscillations, which is a sine omega t plus phi. The phi could be anything. So any point on this circle for some fixed amplitude, if you fix the amplitude. So any point on this circle is a valid solution. But once you start making the capacitor nonlinear, once you put in a chi2 and start pumping it, then you get parametric amplification of only certain phases. So if you structure it a certain way, the sine component dies, and the cosine component is the only one to stay. So your amplitudes will collapse to either some plus a cosine omega t or a minus a cosine omega t. So you get phase 0 I'm sorry, I should have shifted to the laser pointer. So you get phase 0 or phase pi. So that's your bistability. If you're in phase 0, you're in spin up. If you're in phase pi, you're in spin down. Excuse me, I'm sorry. Yeah, so I'm saying here that the cosine components get magnified. So the blue is like plus cosine omega t, and that's spin plus 1. And you get a minus cosine omega t, that's spin minus 1. So these are two stable phases, and sine dies out. So this is the bistability. The way you would implement the connectivity, the JIJs, is through simple resistive connections. So this was originally done by von Neumann in the 1950s. So it is not like fully new. So you have these parametric oscillators, and you have parallel resistive connections to implement J plus 1, and anti-parallel connections to implement J minus 1. And what you want to do is you want to map the power dissipation in these resistors. So we're assuming that the oscillators have no resistors. It's only the connectivity resistors that we have. We want to map the power dissipation in these resistors to the icing problem somehow. So it turns out that when you build it this way, for J plus 1, if you do this, J minus 1, if you do this, you will in fact get a power dissipation that looks like the icing function. But there is a small thing to note here, and that is all the voltage amplitudes have to be equal. If the voltage amplitudes are not equal, you would get something like the voltage amplitudes of the capacitors. You would get something like a spin 0.5 here and spin 1 here and stuff like that. So because that's not how the icing problem works, you have to ensure that all the spins have amplitude of plus 1 cosine omega t or minus 1 cosine omega t. So 0.5 cosine omega t doesn't work. And this idea of this problem with constraints, the icing problem actually has constraints in it, because you have to be either plus 1 or minus 1. That brings us to the topic of Lagrange multipliers. The reason I'm bringing this up is when you study this circuit system, it turns out that this system actually naturally performs Lagrange multiplier optimization. And it's not just this system; it's the optical system that Professor Yamamoto built, and many of the other systems. They all perform Lagrange multiplier optimization. So that's the reason we are just doing a very quick 1-slide tutorial of Lagrange multipliers, or maybe 2 slides. So here, yes, I'm considering a 2-dimensional solution space. You have some function f of x, y. You have these contour lines. So these are the level lines, or the isocontour lines of f. And let us say it increases as you go in. So this line is the best curve of all the curves. And you have some constraint function. You are supposed to choose x and y only on this red line. So which point on this red line has the maximum value of f? That is the constraint optimization question. So let us say you're at this point. If you're at this point, maybe the gradient of f is this way. So the gradient of f has a component along the tangent to the curve. So you take that component, it tells you that f will increase if you take a step. So you take a step and f increased. So you keep doing that, and you reach a point where the gradient of f has no component along the tangent of the constraint function. So there's no, you've reached a stationary point. There's no way you can improve your f by taking steps along the curve. So the point where the gradient of f is basically perpendicular to the tangent of g is the point where you have your local optimum for the constraint problem. So that can be expressed this way. You say, okay, we have a gradient of f. We have the gradient of f at that point, and we have the gradient of g at that point, which gives us the normal to g, and they have to be parallel. That is what the Lagrange multiplier condition says. It says that x and y is a local optimum if there exists a lambda such that this happens. So yeah, we can pull the right hand side to the left and say, okay, the gradient of this modified function is going to be 0 for constraint optimization. For unconstrained optimization, it was very simple. It was just grad f is 0. So you have some function f and you just find its derivative 0. But when you have constraints, you have to modify your objective function by plugging in the constraint and putting in some multipliers. So that's the Lagrange multiplier procedure. For the icing problem, it turns out that we just list everything down. So the spins are supposed to be plus 1 or minus 1. So that means you have G1 is sigma 1 squared minus 1 equal to 0. So there's an equal to 0 here. So that's the constraint on the first spin. You have the constraint on the second spin. You have n constraints. And you have the icing function that you want to optimize. And you can form the Lagrange function. So you just take the merit function, you add in all the constraints with multipliers, and that's it. So you have this Lagrange function. Now, so what we have this Lagrange function of the icing problem. Now what happens? So what happens is something very nice. When you take this sort of structure for your electrical system that emulates, that tries to solve the icing problem, and when you write down its power dissipation function, so the power dissipation is all the dissipation in the resistors, which is what I call the positive dissipation in the resistors. You can write it out this way when you compute it. And we are also going to include the negative dissipation in the capacitors. So what I mean by negative dissipation is the capacitor acts as a negative resistance. It pumps energy into the system. Yeah, it's reducing the power dissipation in a certain way. So you include those terms here, which is the power input terms, the negative dissipation, and you get some big power dissipation function. When you write down the Lagrange function for the icing problem, you notice that they're basically isomorphic. So you have some terms, physical terms here that look like the Lagrange multipliers. And you have some Jij here and there's Jij here. So this basically a one-to-one mapping. So this basically led us to the conclusion that the gains that we are supplying, so this is gain of the system that is being supplied to each capacitor. So the gains are basically equivalent to the Lagrange multipliers. And that's what is happening. So if you have just one gain for all the capacitors, you're basically merging all these lambdas, and you just have one single constraint. And that doesn't implement the icing problem correctly. So to implement the icing problem correctly, you would have to have different Lagrange multipliers, and that basically means different gains on all the oscillators. Okay, so we have this function, Lagrange function that we want to optimize. How does the optimization work? How do we change the sigmas? And we don't know the lambdas also. There are some true lambdas which help us satisfy the Lagrange multiplier condition, which is this. So there's some lambda star here, which helps us satisfy this. But we are not given that lambda star. We don't know what lambda star is. So we have to find both the correct lambda and the correct spins to solve this problem. And the way to do that would be, this is a bit detailed, but it's sort of well understood in the automation community. That is, you have to perform gradient descent of L in the X direction and gradient ascent of L in the lambda direction. So this is just standard gradient descent, follow the gradient. So there's a descent in X happening and an ascent in lambda happening. And that's what we would need the system to do. And it turns out that the system actually does that. So the voltages fluctuate such that the power dissipation goes to a minimum, the nearest local minimum. So you get an evolution equation that pushes X towards the local minimum. And the pump depletion happens such that the lambda moves in such a way that L gets maximized. So it does turn out that the physical system does exactly this: gradient descent in X and gradient ascent in lambda. So yeah, here we're revisiting the systems again to just check that they're all doing Lagrange multipliers. So you have these pulses running around in the optical fiber loop in Professor Yamamoto's system. You have some coupling between them. So you sample the pulses a little bit, multiply them using an FPGA, do something, and re-inject into the corresponding pulses. And that's how you implement Jij. And if you look at the slowly varying amplitude equations in their analysis, it turns out that you get an effective merit function. And in their very specific early case, they were using the same gain for all of them. And that would implement a slightly different constraint. So it would implement optimization of this function on the sphere instead of those sets of like cuboid, hypercube points. So instead of the hypercube vertices, you are optimizing over a sphere. But they changed it later. So this was an early version that they did. But yeah, they changed the gains later on. So Professor Roy Chaudhury's group at Berkeley also does something similar. Their system is interesting because they don't do it in the amplitude space. So this system works in amplitudes on the cosine axis. So you have cosine axis, the amplitudes keep varying, and you want the amplitudes to get pinned at some plus A and minus A. In Professor Chaudhury's system, it's a bit different. He plays with the phase. So he keeps the amplitude fixed. He uses amplitude stable oscillators. So there's a very sharp bell that keeps you at a fixed amplitude. And it's the phases that evolve. And if you look at the evolution equation, it becomes evident that they have a merit function which looks like this, and they have constraint functions for each spin. And this again, basically, this is a reparameterization of the basically does transformator optimization, their evolution equation. And then there is this very interesting method from Professor England and Professor Stolich's group. It is different because it is an iterative method. It's not a continuous time method like the previous approaches. So you have a photonic matrix multiplier. You send some optical pulses in. So the spins are encoded in the amplitudes and phases of the input pulses in the input channels. You have some matrix multiplication that happens, and you have some noise that you add and some thresholding, and you go back in and you do this iteratively. So this is the procedure, and they show in this paper that the ST+1, as T increases, you perform some nice dynamics on the icing problem. So they show that in a certain regime where you have some high noise or in some certain other conditions, you are optimizing this effective Hamiltonian. So the Jij is the standard icing Jij, and this M is some involved function, some involved matrix. But the essence of M, the basic property is M has the same eigenvectors as J. So once you know that, you can play around with this function a little bit. You can rewrite E in terms of eigenvectors of M and J, and you can rewrite this function in this way. So you have some effective merit function, which is the sum of the icing term, which is the first one, and some sort of Lagrange multiplier terms that follow. So this method also, when you analyze it, it sort of boils down to a Lagrange multiplier method. So we looked at this paper, we found it quite interesting, and we wanted to think of it in our own way and see what we could do. So we just took the standard Lagrange multiplier problem, the icing problem, and we relaxed it a little bit. We made it something called the XY problem, which is find the right angles in the plane that minimize the energy of the spins. Instead of forcing the spins to be +1 or -1, assume that the spins are in a plane. So you get some Lagrange function for that sort of relaxed icing problem. And you can write a dynamics that basically iteratively minimizes this Lagrange function. So this is the sort of matrix multiplier that you would need. You would need to implement this matrix in the optical system, and this iteration should solve this problem. We would still need to change the gains. The gains have to evolve because the gains have to perform gradient ascent on the Lagrange function. So there is still some nuance involved here, but this essentially should implement Lagrange multipliers. Yeah, so our method also does the same. So these are plots generated by Patrick, one of our alumni. He basically ran the electrical system for 32 spins, and he showed that yes, the phases all collapse correctly, and you reach the ground state for this small problem. As you get higher, as you reach higher and higher spins, a standard SPICE implementation becomes very difficult to go ahead with. So we changed to a slowly varying amplitude approximation implementation on MATLAB instead of running SPICE. So this was run in SPICE. And we don't reach the global optimum, of course, but we reach a decent local optimum. That's what we've observed using Lagrange multipliers. So yes, so this is just the conclusion slide for this part. We are saying yes, we perform Lagrange multipliers, and the merit function is the power dissipation function of the system, and you go towards its nearest local minimum. So the icing problem is okay, one problem, but can we extend it in some way to machine learning? Was the next question that we got, and this is much more relevant today because everybody's interested in reducing the power dissipation, the power required, the energy required to train neural networks. So we came up with a very simple circuit. That this was essentially a toy problem. We solved linear regression, and because the linear regression merit function is just quadratic, it maps exactly onto icing, and it's a very straightforward extension from icing to get some. This is like 2-bit two-dimensional linear regression. So this sort of circuit does it, but linear regression by itself is maybe not that interesting. The final goal is to find circuits that in some way help us find the right weights for neural networks. So you set up the system, you give in the data in form of the resistors, the training data, and the oscillators collapse to the right weights, the nearest local optimum. So we have some thoughts on that, but it's very immature. So yeah, it's still something to think about, whether this sort of technique can help us find good circuits for neural networks. So yes, so I'm basically saying yes, physics-based hardware helps us perform Lagrange multipliers, and not just that, helps us perform gradient descent at greater speed potentially, and much lower power dissipation. So now for some vector problems, but it's still a work in progress. But yeah, we're trying to show that there's some energy advantage, a proper energy advantage over the digital hardware. Yeah, so yeah, that basically ends my talk. I'm saying, yeah, the future directions, we should try to solve all these problems using physics-based methods. Yeah, thank you. So my collaborators and funding. Thank you for your patient listening.
Awesome.
I'm open
Thank you
for
so
questions.
much. So we have some time for questions. Let me begin with one. In the icing model that you simulated for the circuit coupled resonator implementation, what was your noise model for the phases that you applied to the resonators?
Yeah. So are you talking about this this model?
Yeah, exactly. Yeah.
Yeah, so I don't think so in this particular we are studying that right now. So in this particular run, we didn't have any. We started with some noisy amplitude, but there wasn't continuous noise being added to the system. So there was just starting noise, but there's essentially no noise in the system.
I see. So how do I think of the temperature in that system?
So
Some
this system. So this system by itself doesn't have a. I don't think. Okay, so you're basically asking us to think of this as annealing. Yes, so doing annealing on the Lagrange function will be better than just doing plain gradient descent. I don't think we have done a noisy version of Lagrange multiplier optimization. Yeah.
I see.
So if I understand this correctly, I don't think we have noise here, but we're adding noise in now, and we're trying to.
Okay, that's what I was wondering is the icing Hamiltonian that you show in the, so the energy there that you showed below, if it's gradient descent, why does it, like, why would it
fluctuate? Yeah. So I think yeah. So I'm not very sure what Patrick did in this particular plot. He might have included noise. I'm sorry, I'm not very sure about that. But yeah, I'll look into it after the talk. But yeah, so I think there's one way of thinking of it, and that is you're performing gradient descent on the Lagrange function, which has those amplitude terms and various other terms. You're not performing gradient descent purely on the icing function. So it's icing function plus those constraint terms.
I see.
So it's a different function on which you're performing gradient descent. So it need not like directly lead to gradient descent on the icing function. So that would be one answer. But I should verify with Patrick. Yeah, I'm sorry.
Yeah. Okay. Sure.
I'll find out if you had noise in this simulation. Yeah.
Sure. Yeah. Thank you.
Hi, Sri. Thanks for the talk.
Hello.
Kind of related to this, I was wondering if you could talk a little bit about the restrictions you have on the couplings that you're able to implement with this type of resistor network. Can you get all-to-all and universal coupling?
Yes. So yes. Well, regarding the experimental implementation, I'm not sure whether we can. I've not thought about the fabrication details, but it should be possible to have lots of spins and all-to-all connectivity through resistors. So one like sort of experimental setup that we had in mind was maybe you have one chip with all the oscillators and maybe one chip with all the connections, and you could just connect the two chips somehow and modulate the connections on one of the chips. So I think in principle it should be possible to do all-to-all connectivity. Regarding the values of the connections, so right now the way I showed it, it's just j equal to +1 and -1 that we implemented. But you can change the resistance values, and you can put in lots of parallel resistors in a binary sequence, and you can get arbitrary coupling to some binary precision. So it's not just j equal to +1 or -1. You can do like intermediate j's also. I'm sorry. Does that answer your question?
Yes, thank you.
Okay.
Any other questions?
Should I look at the chat? Oh, no, there's no questions there.
If there are no other major questions for Sri, we can probably switch to the various meetings that were scheduled, for which there will be a separate Zoom link in the schedule. So any last minute questions?
I'll hold mine for later. Okay, thanks a lot, Shri. It's really great.
Oh yeah, thank you, sir. Thank you, everyone.
Thanks everyone for joining us, and see you next time. Shri, I'll shortly share a link for